Alright, so the first task of this project is to graph x squared plus y squared minus 5 on the domain negative 2, 2, 2. So, as you can see below, there is our graph. So, we were supposed to select 3 points at random and find out whether or not they truly exist on this function. So our points are negative 2, 2, 3, 1, 2, 0, and negative 1, negative 1, negative 3. So, how do we know these functions actually lie on the graph? These points actually lie on the graph. So, negative 2, 2, negative 1, negative 1, and 1, 2, those are all points that lie within our domain. So we have that going for us. So we then plug them all into our original function, x squared plus y squared minus 5, to get our respective z values. And plugging in these respective values gives us our z values of 3, negative 3, and 0. Which means they all lie on the graph. So the next part of this is to find out the high and low points of this function. So I hypothesize the min value is 0, 0, negative 5. As if we get more negative than 0, we'd be squaring the numbers, meaning the values would get increasingly positive again. So at 0, that would be the absolute least these values could be, which give us the z value of negative 5. Whereas the max values would have to be some combination of negative 2 or positive 2, as 2 is the absolute maximum value these points can have, which give us 4 plus 4 minus 5, which gives us a z value of 3. So the next task would be to make traces by fixing the x value. So you can see here they are color-coded with the respective value, and the axes are labeled. So the next task would be to estimate where the y values would have a local max or a local min. To do this, we take the derivative of the function with respect to y holding x constant, and that gives us 2y. So to find out what this critical point is, we set 2y equal to 0, and then we divide 2 over, and that gives us the critical point y equals 0. Now, in order to find if this is a local max or a local min, we have to plug in a value less than 0 and a value greater than 0, which I chose negative 1 and 1. Plugging in negative 1 gives us a value of negative 2, and plugging in positive 1 gives us a value of positive 2. Since the value less than is negative and the value greater than is positive, this means that at y equals 0, this function has a local minimum. So we do the same thing with respect to x. As you can see here, the traces are color-coded once again. Now we have to take the derivative of the function with respect to x holding y constant. And doing that gives us the f prime of 2 equals 2x. And as we did in the first problem, we set it equal to 0, and we find that our critical point is at x equals 0. So we find that x equals 0 and y equals 0 are both local mins, meaning that these values are equal. So whenever there's a higher low point, x and y are equal, or at least equal in absolute value. So here's our second function, x squared minus y squared on the domain negative 5, 2, 5. So our point of interest in this function is going to be 0, 0, 0, or the origin. Now, why I hypothesize this is the point of origin is because this is where the function twists in a way. Whereas it's sort of traveling on the x-axis, it travels to the y-axis. So, like we did in the previous problem, we take traces holding, x constant, and we take the derivative of the function with respect to y holding x constant. So that gives us y equals 0 once again. So we plug in our value less than and greater than 0 into our derivative function, which was negative 2y. We find that y equals 0 is a local max. And then we do it once again with respect to x this time. We find that the derivative is positive 2x. So plugging in a value greater than or less than 0, which is where the critical point is in this case, gives us that x equals 0 is a local minimum. Because the value less than is negative and the value greater than is positive. So we find that the critical points in x and y are equal in value, but have different properties. Where in this case, the origin is a local max with respect to y and a local minimum with respect to x. So here's our third and final function. X minus x cubed plus 3y minus y cubed on the domain negative 2.5 to 2.5. So shown in yellow with a orange dot in the middle are the 4 interesting points in this graph. Those are both local max and local min with respect to kind of where they are in the graph. So what are those actual points? So we have to take the derivative of the function holding y constant, and that gives us the derivative equals 1 minus 3x squared. We set that equal to 0, and we solve for x, and that gives us x is equal to negative root 3 over 3 or positive root 3 over 3. So the next step would be to plug in a value less than and greater than root 3 over 3. Plugging in our value less than, which is 0, gives us positive 1, and plugging in our value greater than, which is 2 root 3 over 3, gives us that it equals negative 3. So that means positive root 3 over 3 is going to be a local maximum, as the value less than is positive and the value greater than is negative. We do it again with negative root 3 over 3. So our value less than is going to be negative 2 root 3 over 3, and our value greater than is going to be 0. Plugging in negative 2 root 3 over 3 gives us negative 3, and plugging in 0 gives us 1. Meaning our value less than would give us a negative value, and our value greater than would give us a positive value, meaning negative root 3 over 3 is a local minimum. So now we do the same thing with respect to y holding x constant. That gives us the derivative equals 3 minus 3y squared. So we set that equal to 0 and solve for y. That gives us y is equal to negative or positive 1. So we do the same thing where we take the value less than or greater than and plug them into our equation. Our value less than 0 would give us positive 3, and our value greater than, which would be 2, would give us negative 9. So the value less than is positive and the value greater than is negative. Positive 1 is a local max. We do the same thing with negative 1, where our value less than would be negative 2, and our value greater than would be 0. Negative 2 would give us negative 9, and 0 would give us 3. The value less than would be negative, and the value greater than would be positive, meaning negative 1 is a local minimum. So going back up to this graph, we now know some of the values. The two shown in blue are both critical points, however they are not the local max or the local min of the function. So the next step would be to find the actual points to these local max or local min. We get that by plugging root 3 over 3 and positive 1 into the equation. And that gives us the messy z value of 6 root 3 plus 54 over 27, which that means root 3 over 3, comma 1, comma 6 root 3 plus 54 over 27 is our local max. For the local min, we plug in negative root 3 over 3, comma negative 1, and that gives us negative root 3 over 3, comma negative 1, comma negative 6 root 3 minus 54 over 27 is our local min. So, what have I learned from this project? Traces can be used to determine how a function behaves, kind of like a topographical map. And these values, taking traces and points of interest, usually coincide with one another, like how a mountain peak would coincide with a close together lines on a topographical map. And taking the derivative of the different traces can be used to approximate the local max or min of a function.